Our next talk is, just a second, evolution patterns of some one-dimensional non-uniform cellular automata, which is authored by Sreeya Ghosh, Department of Applied Mathematics, University of Calcutta, India, and Sumita Basu, retired professor, Bethune College, Kolkata. It will be presented by Sreeya Ghosh. Sreeya, over to you.
Am I audible?
Yeah, you are audible. Can you share your screen?
Thank you. Yes, I'll just share. But one participant can share at a time. It's showing. I'll click that.
Yeah, you try. I have stopped sharing.
Okay. Is the screen visible?
Visible.
Okay. Thank you. Good afternoon, everyone. It's a nice opportunity for me to speak on this platform. I will be speaking on evolution patterns of some one-dimensional, non-uniform cellular automata. So the main points I will be discussing will be some preliminaries. I'll just rush through because everyone is very acquainted with CA over here. And I'll be talking about the relation between local and global transition functions of a non-uniform CA, and then patterns of evolution of a non-uniform CA under some transitions. So the CA which I have used over here, or rather which is known, it's a triplet, where the Q is the state set. It's a finite set of elements, the memory elements. Then I have Q to the power Z, that is the set of global configurations. By a configuration, I mean it's a function from set of integers to Q. I have taken here one-dimensional CA, so I have restricted it to a set of integers. And then global transition function is tau, given from Q to the power Z to Q to the power Z. Now, at any time, a global configuration can be denoted by CT, and tau CT will give me CT plus 1. For a particular CA, if C0 is the initial configuration, then my CA will be denoted by Q to the power Z, tau, and C0. That's a quadruple. Okay, some more definitions, some basic ones. If I restrict my set of integers to a subset, then we can define local configuration over it. It will be a mapping from the subset Si to Q, where Q is the set of memory elements, and local transition function will be Q to the power Si to Q. Okay. Now, if I have my local transitions denoted by mu's, so at every cell, we'll have some local configuration with respect to that cell. So it will be mu I minus 1, mu I, and mu I plus 1, so on. So the fully, it will give me the global transition. Now, if I have only two state elements, 0 and 1, then my CA will be Boolean. And since any global configuration is formed of local configurations, if all my local transition functions are same, then the CA is a homogeneous one. If the local transitions functions are not same for all the same cells, then it will be a non-uniform or hybrid CA. And the cells may be finite or infinite in number. If the cells are finite, then we can have boundary elements, boundary cells. So periodic boundary, either or fixed boundaries or reflective boundaries. These are normally the common boundaries. Now, periodic means the last cell will be next to the first cell. And for fixed boundaries, the normal ones which we take is the null boundaried ones. We have a zero padding at both the ends. And the reflective ones is the end ones take the same state as the boundary cells. Okay, so in this work we have used some common transition functions for our non-uniform CA. We have taken identity function, which means over time the evolution, the configuration remains same. Then we have taken constant function, where for a particular state, after any step, the transition function is such that all the cells get to that state for a particular state, whichever my transition function gives. Over here I have mentioned it as Q state, and so after one evolution everyone becomes Q. Then we have used left shift function, which is all the states, the shifts one place leftwards. It can be, over here the example is with one step, one shift, but we can shift m places as well. Similarly, we can shift right side also. Now the complementary function is, if this is for Boolean C, we can have these functions. If my configuration is such that the cells be in state 0, then after evolution they will change to state 1, or if they were in state 1 they'll change to state 0. Now I'll come to the relationship between local and global transitions. Now for a non-uniform CA, we can visualize it as being composed of finite blocks, where each block, within each block, the cells follow same rules, but transition. Now we have one proposition is, if the global transition function be of a non-uniform CA with periodic boundaries be composed of finite blocks of invertible transition functions, then the local transition functions will also be invertible. If the global function is invertible, then obviously the local functions will always be invertible. That's obvious. But however, the converse may not be true. I mean, if the individual blocks be invertible, then it may not imply that globally we will have an invertible function. I've taken one example over here. Suppose we have two blocks. First block has 1 0 1 0 and second block 0 1 0. Then the first block follows right shift and the second block follows left shift. After this block, if we look at the left block, we will see that after it follows one step right shift and again left shift, it will give me the configuration 1 0 1 0. However, I know that left shift is the inverse of right shift. So it should have given me back 1 0 1 0, but it is not giving me 1 0 1 0. Rather, it is giving me 1 0 1 1. So it proves that even if my blocks individually are invertible in nature, global configuration may not be invertible. Now we'll come to some patterns of evolution. Okay, so my full CA is consisting of blocks where the blocks are having different transition functions. We have considered that our blocks are finite in length. Since it is finite, so states of automata are finite. So evolution pattern can be either stationary after some point of time, or they may be cyclic. They cannot be divergent. That is for sure. Now, let us take a CA where the set of transition functions are either identity or complementary or constant to some state q. Then the evolutions can be either stable or two-period cyclic from initial step or after the first step. Sorry. So what are the possibilities? We have two blocks. So what can be all the possibilities? One block follows identity and the second block follows complementary functions. So in that case, the CA will be two-period cyclic from the initial state, because complementary function is cyclic, and for identity it will remain same for all periods. So ultimately the global pattern will be two-period cyclic. Now another possibility is one block follows identity and the second block follows constant function. So over here what we have is it will be stable if the cells following constant functions be at state q itself from the initial step. So the full CA will be stable from the initial step, because after evolution also q state will only remain. Otherwise, if the initial configuration be such that the states are not all q, then after the first step, everyone will become Q for one block, and the other block, because it follows identity, will remain as it is. So after the first step, the CA will be stable in any case. Now if I have one complementary function and one constant function, then we'll have a two-period cyclic pattern from the initial step if all the cells having constant function be at state q only from initial step. Otherwise, it will be two-perioded after the first step. Now we have another proposition. Suppose our CA is composed of 4 blocks. Each block is of finite length, K1, K2, K3, K4, and then K1 block has identity function or constant function. Now K2 block has left shift function, M plus left shift. K3 has N plus right shift, and K4 has that, and K3, which is in between K2 and K4, there I've taken two different possibilities. One is if it has constant function, and the second one is if it has identity transition function. Now for both the steps, what can be my pattern? So in any case, it will be stable after some steps. Why? For the K1 celled block, it is identity or constant, so ultimately that will, we have already seen, that will be stable after from initial step or after first step. Now K3 is again either identity or constant, so that will also have a similar pattern. Only there will be shiftings for K2 celled blocks and K4 celled blocks, and that too, the length of these two blocks are also finite. So after some step, these will always also have a stable pattern. So ultimately the full CA will be stable. Now after how many steps, that we have found out after p plus 1 steps for if K3 is constant, and after p steps if K3 is identity. Now p is maximum of lambda and mu, where lambda is the ceiling function of K2 by n and mu is the ceiling function of K4 by n. What happens is, at every step, say K2 and K4, they have shift functions. So K2 has left shift. So M leftmost cells get deleted from K2, and M cells of K3 blocks, which is following suppose constant function, that enters and takes the place of K2 from the right, and this procedure goes on. And similarly, for my K4 celled block, that follows right shift, so n rightmost cells get deleted, and in places of K3 celled blocks occupy left sides of K4 celled blocks. And this process continues. After some point of time, K2 cells and K4 cells will have elements of K3 cells, and then stability is reached. So I have just, it's not very clear, but I think it's visible. Suppose it's constant, so this will all have Q. So after some steps, this full block will have Q cells. It's K2 celled blocks and K4 celled blocks. And then we'll have a stationary pattern. So similarly for identity also. Now we come to another one. If suppose my non-uniform CA is composed of two blocks of length K1 and K2, such that both are having shift functions of same type of shift. Suppose both are having left shift or both are having right shift. I have shown here using two left shift following both the blocks following left shift functions. But I have used one restriction. The restriction is the length of K1 and K2. They are such that K1 is a multiple of it's multiple of, it's equal to MR1, which means where M is actually the M step shift, which I am using over here. So after some steps, it's obvious the cells will have a stationary pattern. So after how many steps it will have stationary pattern? It will be after R1 plus R2 steps. Now what is happening? Like previous one also, over here both are left shifts. So for first block, M cells will be deleted from left, and from second block, N cells will be deleted from left. And this will go on, and after, since R1 is K1 by M and R2 is K2 by N, so after at most K1 R1 plus R2 steps, all the cells acquire QB state. So they will be stable. So this is happening. What is QB? Now I have taken this proposition with a fixed boundary. Now fixed boundary, I have taken it to be QB. That can be with null boundary also. The same result is not very much feasible with periodic boundaries, but with fixed boundaries and null boundaries, this works fine. So what happens? The boundary element after some steps, R1 plus R2 steps, they acquire, all the cells acquire that step, that state. Now we'll come to another one, where two finite blocks of length K1 and K2 is such that they follow shift functions. One is having left shift, another one is having right shift. This can be applied to periodic boundaries. Now suppose it is periodic, and then what will happen? The full CA will be periodic after some step, after the pth step, which is the ceiling function of K1 minus n by n, and max of this lambda and nu, where lambda and nu is given such. And the periodicity is m plus n by GCD of m and n, where m is the left shift m place, and n is n place right shift. Now what is happening? At every step, m leftmost cells of K1 gets deleted, and from K2 cells it comes and takes its position. For a K2 cell, uh, the right n elements get deleted, and from K1 cells they take their place from the left of K2. Now after some time we will see A1 and B1 as if it will have a cyclic pattern of A1 to AN and B1 to Bn in a cyclic form, where we will have A1 from those K2 cells, and I have renamed it over here, but it will be as if some cells uh, they have a cyclic pattern, some cells of K2 cell blocks and some cells of K1 cell blocks, and that will continue for the time. Okay, this is the outline sketch. Now, if we have these left and right blocks, and we have uniform, non-uniform CA with blocks of such cells, where this left and right shifted blocks continue. Then the full periodicity of the CA. Now we have seen in the previous one, uh, the two blocks have periodicity n plus n by GCD of Mn. And if that blocks continue, then the full CA will be periodic, given by, I mean, just give me a bit, sorry for the disturbance. Okay, I think, sorry. Just,
So yeah, you have to wrap up
I,
in 5 minutes.
yes, this is the last one. Huh? Yes. So the periodicity will be the LCM of all these. So that's it. So that is where I conclude. So we have discussed the evolution patterns of non-uniform CA with some standard local transition functions, and it can be observed that evolution can be treated as a special case. The evolution of a non-uniform CA, the uniform CA can be treated as a special case of evolution of a non-uniform CA, having a single block which follows the same transition. And non-uniform CA is blocks of uniform CA. Thank you. These were some references. I have shared the slides already. So thank you.
Thank you, Sreeya. This is an interesting aspect of study of reversibility and all, using block of non-uniformity over the blocks. That is an
Yeah.
interesting thing. Okay, so what are the properties that you have studied so far over this year? Reversibility and any other thing, or only this one?
See, as far as constant functions are considered, that is not reversible. So we have as yet studied some very special, very transition functions. Not, we haven't explored it globally for non-reversible functions, but except only constant functions we have taken, which is not reversible. Beyond that, we haven't explored as yet. And as far as reversibility is concerned, left shift and right shift we have explored.
Okay. And
Thank you.
if I have understood correctly, in your blocks, the rules inside the block are same, but different blocks are having different rules. Is it like that?
Yes, yes. Inside the blocks, it is as if a homogeneous here, but different blocks are having different transition rules. So that makes it non-uniform.
Okay. Okay, any question from the audience?
Hello, Sreeya.
Yes.
Yes, this is Sumita from India. For each block, you are using different, completely different rules, right? Or
Yes. Yes.
the rule. So, how many blocks are there in your sheet?
See, for the timing, I have studied 2 blocks, 3 blocks, and 4 blocks.
Okay, so
And
it's finite.
yes, finite. And for that left and right shift to blocked ones, I have taken a repetitive configuration as well. That you can go on. But overall, I have still restricted myself to finite case.
Okay, and
But however, if that same pattern continues, the last result which I have done, the same thing will be similar, but that LCM that will go on for an infinite loop, so you will not get a periodicity specifically. So I have restricted it to finiteness.
okay, thank you.
Okay. So is there
Okay,
any
so
more?
is there any other question? If not, then I just thank
So can I
Sreeya for
stop
the.
sharing?
Yeah, please stop sharing.